Welcome back, Chemistry 30. So taking a look at the formal charge bookkeeping part to see what structure it is that we'll actually be keeping. So all unshared electrons count as 1. So if I want to look at the formal charge for carbon and nitrogen, carbon, if we look at here, it has 2 electrons that aren't shared, so we have 2 there. And each of these bonds, we could treat them as I have 6 electrons in total there, 2, 4, 6. Half of them go to chlorine, half of them go to nitrogen, so 3 will go there. So my 3 electrons from the shared part plus the 2 unbonded part give me a total of 5. The number of valence electrons in the neutral carbon is 4. So to use this bookkeeping method, you take the valence electrons, subtract the number of bonded and unbonded electrons, I get -1. So looking at the actual electrons I'm bonded to or shared, that is where this bottom number comes from. For N, there are 2 electrons there, and it has 1 from each of these bonds. So 1, 2, 3, 4, 5 electrons in total that are being shared or unbonded. Nitrogen is a group 5 element, so 5 subtract 5 is 0. So what happens here is I get kind of an idea as to what's going to happen here with bonded and unbonded electrons. Carbon is sitting at -1, nitrogen is sitting at 0. Notice that the sum of the formal charges equals the overall charge of the ion. In this case, the formal charges on a neutral molecule must add up to be 0, whereas those on an ion add to give the charge on the ion itself. If we draw several Lewis structures for a molecule, the concept of formal charge can help us decide which is the most important, which we call the dominant one. One Lewis structure for CO2, for example, has 2 double bonds, as we saw earlier. However, we could also have a triple bond as well, such as this one. So which one is the actual one? Because both of these work. 2, 4, 6, 8, 2, 4, 6, 8. And around the carbon, 2, 4, 6, 8. Over this carbon, 2, 4, okay, so it all works. All of these have an octet, even this oxygen, 2, 4, 6, 8. So if we look at the valence electrons, oxygen is group 6, so it has 6 valence electrons. Carbon is group 4, so it has 4 valence electrons. So 6 here, 6 here, 6 here, and for carbon, 4 and 4. And if we look at the number of electrons assigned to each atom, so if we look at this oxygen, there's 1, 2, 3, 4 electrons that are not bonded. And it's going to take 1 from each of the bonds, so 1 and 2, so a total of 6. Carbon has 1 from each bond, 1, 2, 3, 4. This oxygen has 4 that are not bonded, 1, 2, 3, 4. And 1 and 2 more from the bonds, 1, 2, it's a total of 6. So the formal charge equals 0 in this case. Over here, oxygen similar to what we had over there, 2, 4, 6, and 1 from here with 7. Carbon takes 1 from each of the bonds, 1, 2, 3, 4. And this oxygen takes 1, 2 from these ones that aren't bonded, plus 1 from each of the bonds, 1, 2, 3, so 3 plus 2. Or we do this again, 1, 2, 3, 4, 5. So we have 5 there. So you can see here the valence electrons from the periodic table. Subtract the number of shared electrons and the number of lone pairs of electrons. Here we get 6 minus 6, 0, 0, 0. My valence electrons for oxygen is 6 minus the ones that are in this molecule. So I get -1, 0, and +1. So the total charges work out to be 0 here. The total charges here are 0. So still, which one do we keep? Notice that in both cases, the formal charges add up to be 0, as they must because CO2 is a neutral molecule. So which is the dominant structure? As a general rule, when more than 1 Lewis structure is possible, we'll use the following guidelines to choose the dominant one. So we'll come across this from time to time. The dominant Lewis structure is the one in which the atoms bear a formal charge closest to 0. So one in which all of them are 0 if we can do it. So of course that would include this one because this one results in formal charges of 0 across the board. If that isn't the case though, we look at the Lewis structure in which the negative charge resides with the more electronegative ions or atoms in the structure. So over here, the negative was with the O, which is more electronegative, but then again we have this O over here, which is positive 1, so it doesn't make sense. Why would it be just this O and not this one? So again, we go with rule number 1. If we can get formal charges of 0, that's the structure that we keep. Thus, the first Lewis structure is dominant one because the atoms carry no formal charges and satisfy the first guideline. The other Lewis structure and the similar one, etc., do contribute to the actual structure, but to a small extent. Although the concept of formal charge helps us to arrange Lewis structures in order of importance, it's important that you remember that formal charges do not represent charges on the atoms. These charges are just bookkeeping conventions. The actual charge distributions in the molecules and ions are determined not by formal charge, but from other factors such as electronegativity. So suppose a Lewis structure for a neutral fluorine-containing molecule results in a formal charge of +1. What could you draw from that? So over here I just mentioned, well, it's likely not correct because fluorine, which is the most electronegative atom, if anything, it should have a -1 rating for a formal charge, not a positive one. So that would not be the dominant structure. All right, and just at the bottom of the page here, there's more examples here. I'll just simply go through how we got the formal charges here, because the example here does not show that; it just simply shows the result. So again, looking up first of all the valence electrons, which I tried to line up with this line here. So just simply looking up the periodic table, nitrogen is group 5, so 5 valence electrons. Carbon is 4. Sulfur has 6 valence electrons because it's group 6. Again, nitrogen, carbon, sulfur, 5, 4, 6. And again, nitrogen, carbon, sulfur, 5, 4, 6. And then looking at, okay, what are the electrons doing in the molecule itself? Those are the electrons assigned, and we're going to subtract. Valence, subtract electrons assigned. So if I look at the ends, the lone pairs, each count as 1. So 1, 2, 3, 4, 5, 6 with that nitrogen. And taking 1 from the bond here. So that's a total of 7. So this number right here, which you can't really see, is a 7. 5 minus 7 is -2. Carbon, take 1 electron from each of the bonds. 1, 2, 3, 4. 4 subtract 4, 0. This sulfur, we have 1, 2 that are not bonded. And then 1 from each of the bonds. 1, 2, 3 plus 2 is 5. 6 minus 5, +1. Over here, this nitrogen, 1, 2, 3, 4. Then 2 more from the bonded parts, 5, 6. 5 minus 6, -1. Carbon is 1, 2, 3, 4 that are bonded, so 4 minus 4 is 0. And then sulfur, 1, 2, 3, 4. And then the bonded ones, 5, 6. 6 minus 6 is 0. And then lastly over here, the nitrogen has the 2 that are non-bonded, 1, 2, plus the bonded ones, 3, 4, 5. 5 minus 5 is 0. Carbon, 1, 2, 3, 4. 4 minus 4 is 0. And then lastly here with the sulfur, 1, 2, 3, 4, 5, 6 electrons are not bonded, plus 1 that's shared with carbon, 7. 6 minus 7 is -1. So here are the formal charges that they arrived with by simply looking at the valence electrons from the periodic table, subtract the number of electrons that are in the atoms itself, bonded ones, each counting as 1, and counting 1 from each bond over there. So looking at here, of course, we don't have any that are exactly 0 overall, so we're going to have to look at the next item here. So the dominant Lewis structure generally produces the charges with the smallest magnitude. That rules out the left one because here we have a -2, so it's kind of going to come down between these two here. If you have your electronegative chart, N and S, N is here, S is here, and if we look at that, N is more electronegative than carbon or sulfur, therefore we expect any negative formal charge to reside with the nitrogen. And of course, that makes it this one right here as the dominant structure. All right. Over here I have some at the bottom here. You may wish to try these yourself and just to see how they got these formal charges using the same plan I had up here. Just simply look at the number of valence electrons of each. I guess this is the answer to here. So we have that. Well, actually, this is another practice exercise. So you could run through this. I chose not to, but you certainly could. So number of valence electrons, subtract the electrons involved in the molecule itself. All right, we'll see you again.